Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about the product and quotient rule for differentiation. We're going to start out by letting f of x be equal to x cubed and g of x be equal to x squared, and what I want to do is I want to find the derivative of the product here. I want to do it in two different ways. The first way I'm going to do this is I'm just going to substitute f of x and g of x for what they are, so x cubed times x squared. Then I'm going to multiply them together, which is x to the fifth. And then taking the derivative of x to the fifth is just 5x to the fourth via the power rule that we learned in our last video. The other way that I did this is I thought, there's a limit law that involves products. The limit of a product is the same as the product of the limits, right, individually. So I went with that logic here. The derivative of f of x times the derivative of g of x, again doing the substitution. What was interesting is that at this point, now we require power rule in two different places. This one becomes 3x squared, this one becomes 2x, and I got a different answer. So clearly, these methods aren't the same. This one we know works, right? That's just basic multiplication stuff. We know the definition of f of x times g of x. That's a combination function where you can just multiply f of x and g of x. So what that means is that this other method doesn't work. The derivative of a product is not the product of its derivatives. And so we need to figure out what is the rule for products. To do this, we're going to let f of x and g of x be differentiable functions, and then we're going to let p of x just be the product between those two functions. To find the derivative of p of x, we need to use the limit definition of a derivative. Welcome back, buddy. The limit as h approaches 0 of p of x plus h minus p of x, all divided by h, can be replaced with what the definition for p is, which is f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Now, to go through this, and I can't take credit for what we're about to do, it's not my idea, but generally the proof of the product rule, the derivation of the product rule, begins with this really clever subtraction and addition of the exact same thing, which means that we're not changing the integrity of the difference quotient that we have in this limit. We're adding 0 to it, right? Negative or minus f of x times g of x plus h plus f of x times g of x plus h. Those cancel, but we're writing them in to change the way that this ratio looks. We're writing them in really so that we can do some clever association. If I group the f of x plus h times g of x plus h with the negative f of x g of x plus h, and also if I group the f of x times g of x plus h with the minus f of x g of x, we're going to be able to do some really cool factoring for this stuff. Those have some things that are in common. First, I went ahead and I broke up each piece of the groupings, right? So there were two different groups. I broke them up into their individual fractions, which we can do just by the definition of addition for fractions. And then I factored out a g of x in the first group. Right? I decided to factor it out to the right here. And then I factored out an f of x, there we go, to the right in the second group. Then I applied the product law for limits. So the limit of a product is in fact the product of its limits. So the limit as h approaches 0 gets to be applied to this piece and also this piece. And the same thing happened over here. We applied the limit as h approaches 0 to this piece here and also to the f of x. And you might notice that this by itself is just the limit definition of f prime, the limit definition of the derivative of f. This by itself is the limit definition of the derivative of g. So I went ahead and I did that. I substituted in, right, this literally is g prime times f. The first one was f prime times g. And you might ask, well, how is this just g of x? Well, as h approaches 0, we can just use direct substitution here. H is gone. Now that's just g of x. And then the limit as h approaches 0 of f of x. F of x is kind of as like a constant for the limit as h approaches 0 since it has no h's in it. So that's not affected. We're just going to get f of x there. And so that is called the product rule. If f and g are both differentiable, then the derivative of the product of f and g is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. And dating back to when I first learned this product rule, I always remembered this as f prime g plus g prime f, which is actually using the commutative property on this thing. I kind of switched the order, but that's fine because addition is commutative. But I always remembered it as fig plus gif because it looks like that's what it spells. This is like an I, fig plus gif, and that helped me remember what the product rule was. So if we go back to this derivative, right, that we looked at the very beginning, the proper way to do this would be to just apply the product rule. So f of x times the derivative of g plus g of x times the derivative of x. F of x is x cubed. The derivative of x squared is what I'm multiplying that by, and then I'm adding g of x, which is x squared, times the derivative of f of x. Just instantiating the power rule for both of those situations gives me this, which really nicely gives us like terms. We get 2x to the fourth plus 3x to the fourth, which is 5x to the fourth. And so now these agree. What we knew originally from just using the definition of a product function is now agreeing with what we're getting for the product rule. And that's kind of evidence for it being true. Now, how do we deal with quotients? How would I deal with the derivative of f of x divided by g of x? Division and multiplication are they're inverse operations, but they kind of are one and the same. Division is just a multiplication of a reciprocal. That's basically what it is. So since we know the derivative of a product is not the product of its derivatives, then in this case we can also infer that the derivative of a quotient is not the quotient of its derivatives. Instead, we have to come up with the quotient rule. But the proof is pretty much the same. There's a lot of similarities with the proof for the quotient rule, so here it is. I'll just give it to you guys. If f and g are differentiable functions, then the derivative of f of x divided by g of x is g of x times the derivative of f minus f of x times the derivative of g, all divided by g squared. So square the denominator, square the g of x function. All right, so again, I kind of remember this as fig minus gif, but then now it's divided by g squared. So product rule is fig plus gif. Quotient rule is fig minus gif divided by g squared. That's how I think about it, if you want a fun little mnemonic device to help you remember. So we got these two things. Let's do some examples. All right, example 1. Let's find the derivative of the product between 2 root x and e to the x. So we need to immediately instantiate the product rule. We're going to call this thing f of x. We're going to call this thing g of x. And I'm just going to run it through the product rule. So we've got f of x, 2 root x, times the derivative of g of x, which is the derivative of e to the x, plus g of x, which is e to the x, times the derivative of 2 root x. And again, I should mention, if you're doing the fun mnemonic device with it, which is fig plus gif, you'd have these in the other order. But again, addition is commutative, so it doesn't matter. You're still going to find the right thing. I'm just going based on the stipulated definition, so I'm keeping things in the right order. Well, the derivative of e to the x is just e to the x. So we get 2 root x times e to the x, which I reorganized to look a little bit cleaner as 2 times e to the x times the root of x. And then over here on this side, we've got e to the x there, and then I changed the notation of root of x to be x to the 1/2 so that I could use the power rule on it. When you multiply this monomial, when you bring down the power which is what the power rule says, you multiply 2 by 1/2. That's just 1. I decided not to just put it in there since it's 1. And then 1/2 minus 1, because of the power rule, it gives us negative 1/2. So here we go. We get 2 e to the x root x plus e to the x divided by the root of x. And I think, there's an argument to be made that maybe you want to leave it here, but sometimes you don't want to write expressions with negative exponents. Example number 2, let's find the derivative of x plus 1 divided by x cubed plus x minus 2. This is a quotient. This does not factor into anything that will cancel with x plus 1. So we're kind of forced to use the quotient rule here. We're going to call x plus 1 our f of x. We're going to call the x cubed plus x minus 2 our g of x. And so I'm just going to run it through the quotient rule. First and foremost, notice that the denominator is the same. All I've done is squared it, and that's just how the quotient rule goes. And then in the numerator, we've got our fig minus gif. So we have the derivative of x plus 1 times x cubed plus x minus 2. That's the derivative of our f of x, quote unquote, times g of x, minus the derivative of our g of x times f of x. I went ahead and I differentiated first. So the derivative of x plus 1 can be broken up into the derivative of x plus the derivative of 1. The derivative of 1 is 0 though, and the derivative of x is just 1. So I got a 1 there. Then I left the g of x part by itself. Now we're subtracting away the derivative of x cubed plus x minus 2, which is by power rule 3x squared plus x, and then we're still multiplying by x plus 1. And then I went ahead and I expanded the bottom. So I just expanded this whole thing. Distributing a little bit further, I got that when you FOIL this, or box method, however you want to go, you end up getting this whole mess here. And then I just dropped the parentheses here since we were just multiplying by 1, so that's why I have this. Didn't do anything with the denominator, and then I combined like terms. Right, I distributed the negative sign here, and then I combined all the like terms that I could, and I got that the derivative of x plus 1 divided by x cubed plus x minus 2 is negative 2x cubed minus 2x squared minus 3 divided by x to the 6th plus 2x to the 4th minus 4x cubed plus x squared minus 4x plus 4. And if you're wondering, Mock, why didn't you just leave the denominator as this? Is there any reason that you distributed everything out? No. Actually, in hindsight, I probably should have just left it like this because that looks a lot cleaner. And typically, you want to leave your denominator factored. That helps you see what its domain is. Anyway, I didn't do that for some reason, so there you go. But I probably would, in hindsight, leave it like that. Example 3. Now, I chose this example to showcase that I think once you learn the product and the quotient rule, it's very easy to just tunnel vision and be like, oh, it's a quotient. I got to use the quotient rule. And so you'd start and you'd get this stuff, and then you'd have to do some work afterwards. But instead, notice that this can actually be simplified. All right, I broke it into x cubed divided by x minus 2x to the 1/2. Again, there's a notation change for that, over x. And I can do this just because that's how you subtract fractions, right? They have a common denominator. I've just broken it up into two different pieces. And then you can simplify that though. X cubed over x is just x squared. 2x to the 1/2 over x is 2x to the negative 1/2. And from there, I can just use the difference rule at this point. It's the same as the derivative of x squared minus 2 times the derivative of negative 1/2. So I only show this to point that out. I don't think I even actually found the derivative. No, that's it. So just keep in mind that it depends on what you're looking at, but you may not have to use the quotient rule in certain situations. You may not even have to use the product rule, right? If I was multiplying x squared with some polynomial like x cubed minus 2x plus 7, I probably would just distribute this stuff. And then it's just the derivative of a normal polynomial, which is just sum and difference and power rule. There's no need to make something like that more complicated with the product rule. So just be aware. That's kind of my PSA message. Anyway, so that's it. Kind of a short video just introducing the product and quotient rules and how to use them. Hopefully you guys learned something. Thanks a ton for watching, and I'll see you in the next one.